Hello and welcome to Mechanical Y. Here I have a cannon. Now a cannon is a very simple device. It has a barrel and that barrel is open on one end and closed at the other. Now what you do is you take a propellant such as gunpowder and you pack it into the closed end. Now you take a projectile like a cannonball and you place it in front of the propellant. Now when you set off the propellant, it burns and it generates a lot of pressure. Now that pressure causes that cannonball to accelerate down the barrel towards the open end until it comes shooting out the front. Simple. And a cannon appears to be an instrument of war. But a cannon is also an instrument of physics. This cannon can help us understand various concepts in physics very well. So how is that? Well, first you'll notice that this cannon is on a carriage, and this carriage has wheels. Now some cannons did have wheels, and these wheels tended to be very large because they were dragged behind horses or other carriages by armies around the country, which meant that those wheels had to handle heavy terrain. But this particular type of cannon is the type found on sailing ships, which means that the ship takes the cannon wherever it needs to go. This cannon doesn't need to be moved very far. So why does it have wheels? The answer is Newton's third law. See, when this cannonball fires, this cannon experiences something called recoil, and it rolls backwards. That is because the cannonball has mass, and it takes force to accelerate a mass. And according to Newton's third law, every force has an equal and opposite reaction force. So the force that accelerates the cannonball forward is also pushing the cannon itself backwards. These wheels are on this cannon to absorb this recoil. So this cannon, even though it's an implement of war, is also a perfect demonstration of Newton's third law. So how else can we use a cannon to understand concepts in physics? Well, let's say we make this cannonball very small. And let's say that we load new propellant into the cannon very quickly. So quickly, in fact, that we can fire this cannon almost continuously. Now because the cannonball is very small, it doesn't take a lot of force to accelerate, which means that recoil is very little. And because it loads very quickly, we can fire it and the recoil will continuously push the cannon backwards. So what do we have now? Well, some of you might say that we have a machine gun, another implement of war. But no, we've derived something else. Let's assume that this cannonball is microscopic. Let's say it's on the size of a single molecule. Now let's say that this propellant feeds almost continuously, virtually 1 grain of gunpowder at a time. And this cannon fires extremely quickly. So quickly that you can hardly tell the difference between one shot to the next. So it's being pushed back very slowly, but very steadily. What do we have then? Well, we've derived the operating principle of a rocket. You see, a rocket carries a lot of propellant, and it feeds that propellant in small amounts very quickly into a combustion chamber. And there it burns, just like the propellant burns inside of a cannon. Now, exiting the nozzle of a rocket are the products of that combustion, which function like cannonballs, leaving the tip of the cannon. And that force of the exhaust gases exiting the nozzle push the rocket in this direction. So here we have two things, and they're operating pretty much under the same principle. So how else can we use a cannon to try to understand different concepts in physics? Well, let's say we take this cannon and we put it on a truck. And this truck is moving in this direction at a very particular speed. Let's say it's moving at about 400 meters per second. So this cannon is on a truck moving in this direction at 400 meters per second. Why exactly 400 meters per second? Well, that's about the muzzle velocity of a cannonball fired from this type of gun. And now we can think about what do we observe about a cannon moving on a truck in this direction at 400 meters per second when it fires a cannonball in this direction at 400 meters per second. Well, if I'm standing on the truck next to the cannon, what I see is that the cannon stands still and the projectile goes shooting out the barrel at 400 meters per second. But if I'm standing on the ground next to the truck, not moving with it, what I see is the cannonball comes zooming by me, or the cannon rather, comes shooting by me on the truck at 400 meters per second, and when it fires that cannonball does not move at 400 meters per second, it stops in midair and drops straight to the ground. This is an excellent demonstration of frames of reference. So what else can we use cannonball to understand concepts in physics? Well, Isaac Newton said, let's take a cannon, and let's take a very large cannon and put it on a very tall mountain on the Earth. So let's do that. Here we have the Earth, and here we have a cannon. And he said, let's put a little bit of gunpowder in this cannon and fire it. What happens? Well, the cannonball comes out and it falls to Earth. And he said, what happens if we fire a little more gunpowder behind that cannonball? Well, the cannonball will travel further. Well, what happens if we pack in more gunpowder behind the cannonball still? Well, the cannonball travels further and further still, until it reaches a point where we fire the cannonball so quickly that it actually doesn't fall. The cannonball enters orbit. So Newton used the concept of firing a cannon off a tall mountain and saying that if we fire it quickly enough, we can achieve Earth orbit. And he used this as an example to try to demonstrate different things about orbital mechanics, which he was developing at the time. So what makes a cannon so ubiquitous? What makes us want to analyze a cannon and not some other implement when we're trying to understand physics? Well, a cannon is very simple. It is a very simple device, and when I'm trying to understand a complex physical principle, I want to be able to test it using a simple device. Second of all, cannons are something that people had a lot of experience with in the 1800s and 1900s. So if you described a new physics concept in terms of how a cannon operates, people were more likely to understand what you were talking about. Third of all, a cannon fires a cannonball, and that cannonball travels very rapidly, and it travels a very long distance, which means that we have a lot of time and a lot of space to make observations about that cannonball and where it goes and how it travels. If we fired something like a ping pong ball out of a low pressure air cannon, well, it's not traveling very quickly and it doesn't go very far, so we don't have a lot of time to make observations. Furthermore, the projectile itself is very, very heavy, which means that it's not so susceptible to things like air resistance and crosswinds. If we fired the ping pong ball, well, crosswinds and air resistance might blow it around and might contaminate our calculations. Third of all, the cannonball is round. It's a sphere, and spheres are very convenient shapes to analyze mathematically. Fourthly, the cannon accelerates that sphere, that cannonball, very, very rapidly, almost instantaneously, which means that we can treat the firing of a cannon as an impulse, something else that's very, very convenient to calculate using mathematics. So we see that a cannon has a lot of features about it that make it very convenient to represent the events that are going on using simple mathematics, and when we describe what's going on to people who may not be physicists, they're more likely to understand what we're talking about. So, a cannon may be an instrument of war, but it is also an instrument of physics. And please keep that in mind. Well, thank you for watching. I hope you found this interesting. Please like and share this video if you did, and please subscribe to stay up to date on new content.